Greetings, my name is Alexandru Cioban. My master's thesis consists in understanding topological waves in 2D plasmas. I'm working under the supervision of Professor Terces at Técnico. This is a relatively new territory, so we use ideas from topology, condensed matter physics and fluid mechanics in the regime of plasmas. In condensed matter physics, one studies elementary excitations propagating inside the material. These excitations are modeled by wave packets with a dispersion relation omega and wave vector k. Depending on the form of omega, the excitations may be called electrons, photons, phonons, plasmons, rotons, and so on. For an electron moving in a crystal, the wave packet is an exponential times an envelope, which we call a state. The wave vectors add vectorially, and if the material has a periodic structure, analyzing the physics in the cell that repeats itself suffices due to translational symmetry. So it makes sense to Fourier transform the repeating structure into k-space. Inside this space, every point represents a plane wave and every line is called a mode. Now, as every student of engineering knows, any physical system takes the path between fixed points that minimizes the integral of a Lagrangian. This seems to violate Newtonian determinism because we need to know the final point in order to calculate the point in between. It therefore shouldn't be surprising that the same principle applies in quantum mechanics. Legendre transforming the Lagrangian into Hamiltonian H, we find that our U satisfies Schrödinger equation, whose solutions are multiple functions u and multiple omegas, which we call bands. We solve the equation and plot the omegas over this abstract k-space. Now suppose we vary with knobs in a laboratory the parameters k around the whole boundary of the k-space. The u's and omegas will vary to satisfy Schrödinger throughout, and in particular different bands won't touch. In the end, we expect to get the same u, however, we find that it comes with a phase factor. This is akin to parallel transporting an arrow by a curve. In a curved surface, it doesn't have the same orientation at the end, despite being at the same place. The phase can be computed by a line integral. Notice gamma doesn't vanish because the state at k plus dk will be different from the state at k. We can think of this phase factor as arising from curvature in a subspace of our Hamiltonian, because this integral reduces to a flux over the interior, like so, which can be related to the number of holes of a surface. Thus, it is a topological invariant, characterizing each band. We call it a Chern number. Now over to fluids. We do the same procedure of Fourier transforming space, however, we don't have a lattice. Fourier space extends to infinity, which doesn't allow for a trivial definition of curvature because we'll integrate over non-physical values. Remarkably, including additional physics into the Hamiltonian solves the problem, but now we observe unidirectional waves at the edge of the system. Here, the wave of fluid propagates only along the circular edge and doesn't scatter off the defect, because it is topologically protected. The plot in k-space is similar to this, where gapped bands of different topology are connected by a line that represents the wave, shown in real space. Heuristically, boundary conditions at the edge make waves scatter from the bulk, as the change in topology is achieved by the touching of bands through the mode. It is natural to conjecture that the topology of the system in the bulk determines the number of chiral modes at the interface. Given all this, I'll be dealing with models of plasmas, which, for our purposes, is a material whose distribution of ions is such that a disturbance in one side is able to propagate throughout due to electromagnetic interactions, easily forming a matter wave. My work will begin by extending these concepts to a fluid of electrons where there is non-vanishing electric field, try different forms of dispersion relation achieved with a field transistor, see what kind of waves appear at the boundary, and in particular, check if the bulk boundary correspondence holds. Thank you.